Welcome to the Knowledge Graph seminar. As you know, the focus for this week is on knowledge graph data models. Last week, I gave you an overview of both property graph and RDF data models. Today, we are pleased to have two experts on each of those two topics. Dr. Petra Selmer, she works for Neo4j in the query language design group, where she is involved in the development of Cipher, as well as she is contributing to the international standardization efforts for graph query languages, as well as for graph query extensions to SQL. Professor Ozu is a faculty member in the Department of Computer Science at University of Waterloo. Throughout his career, he has been working on distributed database systems. He has written a textbook on the topic, as well as he is the editor of the Encyclopedia on Database Systems. His contributions have been recognized by multiple professional societies, including ACM and IEEE, as well as through numerous awards, such as Lifetime Achievement Award and Test of Time Award. We are hoping that each of these speakers will give us about 30 minutes of technical overview, which will leave us about 20 minutes or so at the end to ask them more in-depth questions. We are going to begin with Dr. Selmer. Petra, over to you.
So just showing the screen. Right, so hopefully everybody can see my screen.
Yes, we can.
Okay. Right, thanks very much, Veena, and I'm very, very pleased and happy to be here. So thank you for having me. So over onto the presentation. So just generally a very quick outline of the talk. So what I'll be doing is giving a very quick recap of the property graph data model. So I know in a previous lecture, you guys were introduced to the model, but just in case you need a bit of reminding, I'll just whiz through that very, very quickly. And then I'll actually go over onto the Cipher query language, and I'll be focusing in particular on the read-only portion of Cipher, and in particular also on the bits of the read-only portion of Cipher that really gives a lot of rocket boosting to actually reading and accessing graph data. I'll then actually mention a little bit about the Open Cipher project. So we've got sort of these terms, Open Cipher and Cipher. What do they actually mean? So Open Cipher is technically the project that actually fosters the open version of the language Cipher, and more about that in a bit. And then I'll actually be introducing a GQL, or Graph Query Language, and this is actually the query language that we are going to be standardizing alongside SQL property graph query extensions in under the auspices of ISO IEC. And to actually end off with, I'll be walking through a few of the proposed extensions. We'll be making it both into the next version of Cipher and also into GQL. So just to start with the property graph data model, there are basically three constructs that compose the property graph data model. The first one is a node, and that's actually a synonymous term with Vertex. So if you come from a very mathematical background, you're probably more familiar with the latter term. And essentially this represents some entity within your graph, within your domain. And essentially in the property graph data model as it currently stands at the moment, you can actually have that a node can have 0 or more labels. Also, a node can have 0 or more properties, and these are essentially name value pairs. And one thing that's actually worth bearing in mind is that two nodes that have exactly the same set of labels can actually have completely different properties. So that's actually something that very much plays into the heterogeneous nature of graph data. So now we've got nodes in our graph. So to actually augment that and to really make it a graph, we actually have the second construct, which is a relationship, which is synonymous with edge. I tend to actually say edge more often than relationships, and gives it a shorter word to say. But anyway, they're synonyms, interchangeable. And essentially, this is the construct that really makes your graph a graph. And it essentially adds structure to your graph, and very importantly, it provides semantic context for your nodes. So your nodes on their own are not very useful, but once you actually have edges between them, you actually start building up a picture of what it actually all means and how it all fits together. Looking now at sort of the attributes of an edge, essentially what an edge can have is it must have one and only one type. And you can think of this as being synonymous, or analogous rather, to labels for nodes. But unlike a node, an edge can only have one type. Also, an edge has got to have a direction. So there's always a sort of an outgoing node and an incoming node. relative to the edge. And also, just like nodes, you actually could have properties. And just very importantly to mention, both for nodes and for edges, they can have 0 or more properties. So you do actually sometimes get circumstances where you don't want to have any properties or any data as such attached to your node or edge. And that's certainly something we've seen sometimes. And just to kind of beat home the fact as well that an edge absolutely has got to have a start and an end node. And of course, we do actually cater for self edges. So an edge can actually have the same node, both as its starting and as its ending node as well. And just to kind of delve a bit more deeply into a property, essentially that's a name value pair or a map that can actually go on nodes and edges. And this is actually where all the data will be stored. So essentially it can be something like name, age, weight, etc. And usually actually the name of the property is a string. So it actually like it should be the string name or the string age, etc. And then the value can be any one of a certain number of types. It can be an integer, sort of a decimal, a string, even a list, etc. Right, so that's actually the property graph data model. So hopefully that's actually kind of got everybody's feet a bit wet. And actually that leads us nicely into Cipher, the query language itself. So introducing Cipher, so this has actually been around for quite a long time now. It was actually developed by Neo4j way back in 2010. And what actually happened is that 5 years later in 2015, we actually opened it up to everybody. So over the years, obviously, lots of different graph database vendors have come to the fore. We actually thought it's such a great language, let's actually spread it and actually allow any implementer, whether they be practitioners in industry or whether they actually be researchers, of which we've seen quite a few, they can all actually implement Cipher. And we certainly created this project in order to actually allow for that to actually happen. So as I said, more about that later on in the presentation. So just to talk a bit about Cipher's characteristics, I'll just focus for now on the bottom half of the screen. So very much in footsteps of SQL, and I should also mention Sparkle as well. There are lots of syntax and capabilities that we've inherited from those languages. So for example, we've got DQL for reads, and just again, I mentioned that that's a focus of this talk. We also have DML for updates and for inserts and deletions. We also have a capability of actually defining and specifying and managing constraints and indexes. So you may be actually now wondering why Cipher. So essentially what it grew out of was actually the notion of defining a declarative graph pattern matching language that actually is very intuitive for users to use. That actually adheres to a lot of modern paradigms. And in fact, I'll be talking about one of those in a while. But essentially, the unique selling points, if you like, of Cipher are the fact that graph patterns are very easily expressible. That's essentially the beating heart of Cipher. It's a first-class citizen. It actually allows you to formulate very easily recursive queries, variable length relationship chains, and the ability to actually return paths. So if we actually take a step back as to why somebody would actually use a property graph data model instead of, say, a relational database, the sorts of use cases you'd be looking at using a property graph data model for would be when you actually want to, for example, understand relationships between entities, especially in cases where you've got lots of different kinds of entities and lots of different relationships between them. You also would be looking at using the property graph data model for when you have lots of self-referencing to the same kind of entity, or if you want to actually explore relationships of varying or unknown depth, and also when you actually want to discover different routes or paths through your data. And so because of these four sort of intrinsic motivations for using a property graph database, Cipher was created specifically to actually be very, very valuable to actually fulfill those needs. So that's actually where we are coming from. So to actually start off at the beginning, the absolutely basic inner core of Cipher is the notion of a pattern. And essentially, as you can actually see on the slide, we actually have the fact that this notion of ASCII art, so you can actually sort of, if you squint a bit, you can sort of see that the circle that you've drawn on the whiteboard or napkin or whatever it is that you've drawn out your domain on can actually be represented by round parentheses, for example. That would actually represent your node. Your edges would be sort of these arrowed constructs. So it's very much ASCII art first, and that's actually how the patterns were born out of that. And just to actually reiterate how important this notion of patterns are, they're not only in the matching, i.e. in the reading portion of Cipher, and actually you've got a read clause down at the bottom left of the screen, they're actually also used a lot in updates and also in all the DDL statements and definitions too. So it's pretty much everywhere. That's the DNA of Cypher. So let's maybe just delve a bit more deeply into actually how you would use these patterns in a read-only context. So central to this is the notion of a match clause. And essentially what we have here are two keywords, so match and then a pattern. And return is actually the projection clause. So what you actually have in the match pattern, sorry, in the portion of the query following the match statement is a pattern. And that essentially is composed of two nodes separated by an edge. And actually, I'll just work left to right and just describe what's actually going on there. So on the left-hand side, we actually have the fact that we are starting at a node, which has a person label on it. And we're also expecting that that person labeled node must have a name relationship. And furthermore, if it does have a name relationship, the value of that name relationship must be Dan. Then what we're doing is actually finding all nodes that basically correlate to that particular node pattern. We're actually examining them. Do any of them have an outgoing loves relationship? I.e., is there any edge going out from that node that actually has a loves edge type on that? If there is, then we actually examine the node on the other side. And essentially there we don't actually have any predicates at all. All we have there is a node variable, and that's actually the node that we actually then return in the return statement. So essentially just delving a bit more deeply into what the various different versions, if you like, of node and relationship patterns that you actually have. You actually have on the left-hand side column all the various flavors of node patterns. So all of them have got to be surrounded by round parentheses. If you actually use any identifier before a colon, that's always going to be your node variable, and you can actually use that as an alias to refer to that particular node later on in the query, especially when you actually start building up your queries by using multiple parts. If you actually want to specify a label, you then actually have got to use a colon and then a label. And as I mentioned before, nodes in the property graph data model can actually have 0 or more labels. So say, for example, you want to actually find a node that has both the label person and employee. What you'd actually specify is colon person, colon employee. And that actually says, find me all nodes that have both of those labels on. And then actually you have the fact that nodes can have properties as well. And very, very synonymously, the same goes for relationships on the right-hand side. And now, if you actually are reading, if you're using these patterns for reading, i.e. in the match clause, what those property map literals will actually be, i.e. those are the curly braces prop dot value, those will actually act as equality predicates. So in your read statement, by actually saying something like n label prop value, you're actually saying that that particular node must have a property with that name and with that value. But you can also use it for updates, as I mentioned earlier. And in that case, what you actually are doing in that sense is that that property map literal, sorry, will actually be inserted or updated into your node. So use exactly the same paradigm for mutating your graph. So looking a little bit more into a more sort of a complicated read-only statement, what we actually have here is, this is actually the way a query actually is structured. So you actually begin, so this is unlike SQL, you actually begin with what you actually are trying to look for. So here you've got your match statement, and this is just a bog standard triple node edge node pattern. Then actually can filter with predicates. So you can use either a property map literal if you're interested in a property equality predicate, or you can actually use a where clause like you do in SQL. And this actually is a bit more advanced because you can actually use inequality predicates, and you can actually start tying up property values from all the different nodes in your pattern in the match. So it's a lot more powerful there. So anyway, that's very, very familiar to users of SQL. And then you actually you almost end off with a return statement, and that essentially is your projection clause. So that is analogous to a select statement in SQL. And you've got to hand all the various functions that you have available in SQL, like upper and aggregations and all those sorts of things. And then also, inherited from SQL is the notion of ordering and slicing and things like that. So that's pretty much, if you like, the most basic query that you can actually have. So one thing to actually bear in mind is, if you look at the, pardon me, the box in the top right corner, is what's actually very, very nice is you're actually able to delineate quite complex shapes, if you like, in your pattern. So just having a triple is not very interesting. So the me per friend is not very illuminating. But if you actually look at the match example I've given in the gray box, you can actually start to transcribe much more complicated shapes. It's not just linear patterns, but actually you can start transcribing star-shaped patterns or T-shaped patterns like this one is. So you have a match A, B, C. So that's actually 3 nodes separated by edges about which we do not care about anything, so we just have it as a dash. We don't actually provide any more information, comma, another pattern, B to F. And actually what will happen is that the 2 B nodes will match to the same node in the graph. So essentially what you've transcribed is a T-shaped pattern. And you can actually continue adding more comma separated patterns in this way. So this actually gives you a lot of expressivity and flexibility with respect to transcribing complex patterns that directly match your shape of graph that you want to match. So I believe in a previous presentation, Vinay had actually introduced you to the basic pattern matching capabilities in Cipher. So what I actually want to do on this slide and the next few is actually focus on the more advanced pattern matching features. So this is actually where it differentiates quite a lot from SQL. So what we actually have starting up at the top is we start with a basic triple. I'll just call that, sort of borrowing from Sparkle heavily here, node edge node. That's maybe not all that sort of novel. But where it starts to get really powerful is when you actually add something called transitive closure or variable length path matching. So in the very first query up there, you'll sort of see match me friend star first. And what that actually will say is traverse one or more friend relationships. So you start at the node on the left-hand side, me, then actually you'll fan out and actually start to traverse as many of the friend edges going out from there or coming in from there, because that's actually an undirected edge, for as many friend edges as you have in your graph. And you actually get returned all the me and your direct friend, or your friend of a friend, or your friend of a friend or a friend, etc., etc. And then that's bounded in the size of the graph where you have the transcribed by friend edges. You can actually then have various flavors of that, in particular bounded transitive closure. So for example, the second one there is actually traverse 2 to 4 friend relationships. So what you actually are specifying there is me, friend, star, so you're indicating it's another variable length path. What you're actually saying is at least 2 friend edges, but at most 4 friend edges, and bring me back all results that conform to that. And what we also then have actually as a third flavor of this variable length pattern matching paradigm is the notion of actually traversing a union of likes and no's one or more times. So the actual me colon likes pipe character no's star essentially means one or more times any combination of likes or no's. So likes, 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 no's, 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 likes will be returned, as well as likes, no's, etc., etc. And again, that's bounded in the size of your graph. And you can obviously combine all these various bounds together as well. And there's no limit on the number of edge labels that you can express a union over. So that's variable length relationship patterns. And as I mentioned, that's actually really, really super useful. It is possible to do that in SQL. Certainly in some variants you have common table expressions. It's just much more difficult to do that. You can obviously also simulate that with unions, but that starts to also get very cumbersome. So anyway, this is a really good way of actually expressing quite a lot of complexity in quite a short space of text. And the next portion is actually the ability to actually return paths, which is something that is not possible currently with SQL, at least to my knowledge. So if you actually look at the returning paths segment and the first query there, match P equals, and then there's some path over there. And by the way, these things needn't just be node edges nodes. You can actually start composing chains for as long as you want. But essentially, match P equals some path, return P will actually return all the paths conforming to that particular pattern. And what you can then actually obviously do after that as well is order it by length and things like that. And actually what P will look like is it will be in order the nodes and edges returned in that way. And then we actually also have functions on paths that you can actually invoke. Say, for example, return nodes of P. And what that will actually do is just return you the nodes that actually were part of that path. So if pattern matching is the absolute beating heart of Cipher, something else that follows very much closely after that is the notion of linear composition. And that's a sort of notion of top-down flow and query parts. And essentially, I'll try and take it apart using that example query over there. So what we actually have in Cipher is the rule that a query needs to end with a return. But if you want to actually break up your query by doing, say, aggregations along the way, or if you want to mix reads and writes in your query, which is also possible to do with Cipher, we actually use a keyword or a construct that's very similar to return in that it also projects, but it's like an intermediate projection. And that's actually denoted by this with keyword over here. So I'll just walk you through that query over there. So what we actually do in line 1 is we do some sort of match, and what the results of that match will actually be placed into a binding table. That binding table will then be used as an input into the with statement in number 2. And what with will do, as written over there, is it will actually pass through the variable me, and it will pass through the aggregation of, the count of all of the friends as friend. But what that means is, in line 3, what's available to that match is the variable me and also the variable friends. But the variable friend won't be available. Essentially, with acts as a gate. If you've not actually written a variable in your with statement, it is no longer visible after that query. So in line 3, we then actually continue matching further on the table of results produced by line 1. And so in line 3, we actually take the me's that were previously matched. They all had to have a label of person and some name, which is parameterized, and then matching further on. And then we finally actually return that count, that aggregation from line 2 as friends. And now we're also counting up the enemies. So hopefully that actually gives you a notion as to what's meant by linear composition. So the idea is basically each function, you can look at each function as a, each clause as a function taking in a table and actually transforming it in some way, maybe adding more rows or maybe adding more columns, and then actually passing it down through to the next clause. And with acting as a horizon. What we actually call in Cipher the 2 different query parts. So line 1 would be a query part, lines 3 and 4 would be another query part, and with just basically glues these guys together. And that's actually been a very, very useful paradigm to have, very much borrowed from modern programming languages. And we have found that the top-down writing and reading order has actually proven very useful. And that's certainly something that our customers and developer community very much appreciate being able to do. So just a quick note.
So Petra, we have about 10 minutes left.
Right, okay, I'll hurry up on that. Yeah, I'm about halfway through. So just to give you a quick example of quite a sort of complex graph of lots of different events happening and an actual query that you can actually pose in quite a short number of lines. So actually this is initially inspired by the H1N1 crisis back in, certainly I was working in a data collection in the UK on this back in 2009. So anyway, I had absolutely no idea it was going to actually be foreshadowed by current events. But anyway, it actually just shows the suitability of modeling complex domains using graphs. And actually in a few short lines, you can actually express quite a complicated query. Anyway, there won't be time to actually walk through that. So I'll just move on very quickly. This is actually just showing SQL versus Cipher. In particular, I want to actually focus on the fact that the Cipher statement has transitive closure statements. So actually it's a variable length part. And it's actually, this is just showing again how much longer it takes to actually formulate that in SQL and obviously the time needed to absorb and parse it. Right, there's also a little bit about the Neo4j Cipher query engine. This is actually very similar to relational database engines. So essentially there's nothing really spectacularly novel happening here, but essentially what we have is that a query string comes in, it's parsed, extra semantic analysis is performed on the resultant abstract syntax tree. We take the usual route of actually finding the cheapest logical plan using some statistics that we maintain in the database, coming up with an optimal logical plan, and then we transform that into a tree of execution physical planning operators, and then we execute the query. So one thing I will say is that because it's a graph, obviously, we actually did have to add an extra operator or two over and above the usual relational operators. And that was in particular to do with expanding outwards from a node. Right, so just a very quick mention on the Open Cipher project. So this was the bit I mentioned earlier on, in that we actually found that Cipher was just a very, very useful and good thing to have, and let's actually spread it across as many graph database implementations as possible. So anyway, a few links over here for you to look at afterwards. Certainly what I can say is that the language artifacts, so the provision of grammars, of formal semantics, especially the TCK or Technology Compatibility Kit, certainly did a heck of a lot to actually rocket boost implementation. And actually on the website, you can see the full list, and probably there are many others, of Open Cipher implementers. And that's just showing you actually what one of these tests look like. And we've got well over 2,000 of them. So it's actually a really great way of ensuring that your implementation absolutely does comply with Cipher semantics. So onto graph query language, or GQL. So essentially, as Vinay had mentioned in the introduction, this is actually an ongoing effort to actually standardize a new graph query language, property graph query language, under the auspices of ISO IEC. And how this actually came about was that a couple of years ago, we had the following situation, exemplified by the three tabs up at the top. We actually had that as more graph database implementations are coming to the fore, we were starting to see lots of different languages starting to arise. And this is not really great for industry, having sort of multiple versions of languages that have great intersection with each other. So it's actually time to take all these languages, all the commonalities, but also all the extra added bits that each one added, which made it special, and actually rather fuse that into a standard graph query language. And that is how GQL was born. And this actually shows a little bit more about that process. So this is the first international standard database languages project since SQL was incepted in 1987. So up until now, SQL, any new language that's come about, or any new paradigm that's come about, like XML, has always been piggybacked on top of SQL. So this is the first time that a standalone language that sits alongside SQL rather than on top of or underneath or next to, sort of tucked away to the side of SQL, has actually happened. And the vote actually went through successfully on that in 2019. And essentially, this is what I, my colleagues, and a lot of other industrial partners across all the major vendors have been working on for the last couple of years. And that's to essentially do the work on the following two. So we actually have that SQL obviously is a language that's ever evolving, and graphs have actually become huge everywhere. And probably it's no surprise that SQL itself is also looking to have something called property graph query extensions, or PGQ. So this is going to be the next new part of SQL. It's slated for release in 2022. And what will happen here is that essentially you'll be able to virtualize a graph from an underlying relational database. So essentially you'll be able to map from your tables a virtual graph that you can actually then query using exactly the same querying capabilities that you'll find in GQL, all of which is very, very heavily influenced by Cipher. So those two, the pattern matching capabilities, the reading of graphs, will be shared by the two languages. And that's where you actually find that the same people are more or less involved in both groups. What GQL will also give you, though, is loads of other things, such as DML, allowing for multiple graphs, and actually being able to form views and graph projections and graph scheme and all sorts of other things as well. Also slated for release in 2022. And we're hoping that actually future versions of GQL will then actually take graphs as a sort of substrate and then just take it much, much further, such as looking at streaming, temporal graphs, etc. This is just a very quick picture just showing this sort of, just a really small snapshot of all the various languages and all the various academic efforts as well that have actually been undertaken over the last 30 years or so, that's actually leading into the formation of GQL, as well as what each language brought in particular to the picture. And just very quickly, I'll just mention the extensions. So this will be forming part of GQL, the standard, but it will also actually be coming in a future version of Cipher as well. So essentially what we actually have here is the notion of repetition of path patterns. So instead of just being able to repeat edge labels, we'll now actually be able to repeat whole patterns as well. And actually here's an example showing how the query actually evaluates. Probably those of you who are very familiar with Sparkle, this is analogous to Sparkle 1.1 property paths, but what it actually will also consider are property predicates and node labels as well. And this is just showing again some of the various extra knobs and twiddles you can actually apply to that, but also things like label expressions, etc. One will also be able to configure pattern matching semantics. So you'll be able to actually express whether or not a path is applied under node isomorphism, edge isomorphism, or homomorphism. And there are different reasons to actually allow each of these in different contexts, depending upon the domain. Also, as you'd expect, path pattern output modifiers. Do you want all paths? Do you want all shortest paths? Do you want any shortest paths, etc.? And data types as well. So where it's very similar to SQL, we'll be reusing SQL exactly as is, but then also be extra things as well, such as a lot of nested data, and in particular, the graph-related data types. That is nodes, edges, paths, and graphs. Schema as well. So traditionally, Cipher has been schema-free. This has been a really good thing. But we also do have use cases where the notion of a schema would actually be a good thing, and that's especially more mature domains or domains we actually have data governance or data quality strictures. And probably just second last is actually the notion of having the ability to refer to and manage multiple named graphs, and to also project graphs, and also to actually allow for graph composition. You can actually undertake combinatorial operations across multiple graphs to form, say, a new graph, and you say maybe project a subgraph out of that graph, etc. And this actually would allow you to set up very complex workflows. And yeah, that will certainly be a very powerful thing. And this is where the compositionality of it. So the output of one query can form the input of another query. And that's essentially one of our goals as well. And this is just some key papers that we've been looking at recently. But I've got to say there are many, many, many more, and there's just not enough time to give space to them, unfortunately. But we definitely are standing on the shoulders of giants in this regard. And thank you very much for your attention.
Thank you, Petra. That was an excellent overview of Cipher and extensions and standardization efforts. We will take the questions at the end, but for now, we will move on to Professor Ozu.
Okay, let me share my screen, and hopefully it will work properly this time. You can see it?
Yes.
Good. Okay.
Perfect.
All right. Thank you for the invitation. It allowed me to get my thoughts together on this topic. We've been working on bits and parts of it, and this was an opportunity to put an entire talk together. You will notice that I have far more slides than I can cover in 30 minutes. The idea was to have an internally coherent presentation, but I don't intend to cover all of it. You can use the slides for later on as background, and I hope you won't mind me skipping through a bunch of slides or going fast on some parts. The idea is to give you an overview of how distributed RDF and Sparkle execution, what works have been done. So I should say that all of my work in this area is done jointly with two colleagues, Lei Zhou at Peking, Peng Peng at Hunan, and Lei Chen at Hong Kong USD. And these are either my former students or my academic grandsons. My work with my own students focus on property graphs, mostly the last few years on streaming property graphs, but that's a talk for another day. So the RDF use cases are quite common. You've probably focused on all of these, and RDF is one of the building blocks of knowledge graphs and the semantic web, and the linked open data in the latest count is about 1,200 data sets, and nobody really exactly knows how many triples there are. But the best guess I could find is over 100 billion triples. My guess is that that's conservative, because UniProt on its own, which is the biological the knowledge graph in itself, or RDF store in itself, reports over 84 billion triples. But the RDF data sets are growing, and the growth in this case is fairly fast. LOD's growth from about 10 years ago to today has been substantial. And all of these lead to the issues of managing this RDF data. So for people like me who are fundamentally data management researchers, when you give us a data model and a query language, we are in our zone. I think this is where the data management issues come up. We could look at declarative query processing, and the obvious solutions are not efficient. So the database community or data management community typically focuses on efficiency in query execution. The initial systems for RDF were single machine or centralized, but with the growth in data set sizes, we've gone to distributed solutions, what I call scale out, which is on the left, which is really you have a large RDF data set, and to get better performance, you typically partition this data set over multiple machines and then look at executing Sparkle queries in parallel. And on the other hand, the independent data sets have been growing with a lot of RDF data sets, and these have their own owners, and they have their Sparkle endpoints, and and they do want to keep and maintain their own data. And for that type of an environment, federated solutions have been developed. So that's the setting for the distributed Sparkle or distributed RDF. There was at the recent EDBT conference in about 2 weeks ago, Katja Hose gave a very nice keynote on knowledge graphs, and the way that she categorized the systems is depicted here. And she basically talked about centralized and then client server and so on to streaming. I worked on this a little bit more, and I think I like a little bit finer granularity. So from my perspective, there is the centralized, and centralized ones can be either more or less relational. So take the triple table and work with that, or they could be graph-based. I'm not going to be talking about that. Or they could be scale-out solutions which have a number of different alternatives, or they could be federated solutions where you have Sparkle endpoints from which where you can actually execute Sparkle queries, or some of the endpoints may not be Sparkle endpoints. They can store RDF data, but have no processing capability. And streaming systems have started to appear as well in terms of the RDF streaming. So what I'm going to do today is only talk about part of the scale out, the query partitioning cloud-based partial evaluation, and the federated systems. The others I will not touch upon. Katya's keynote is going to be put, I think, on YouTube. I don't think it is there yet, but if you check EDBT 2021 conference website, you will probably find when that goes online. I would highly recommend watching her presentation. So the outline of the slides, not the talk necessarily, is it starts with an Rdf introduction, which I won't go through because I understand you've covered the basics of Rdf. I have 2 points there that I want to touch upon that are important for the later discussion. Then I have some overview slides on centralized systems. Again, I won't touch upon those, and then I'll jump into scale-out systems. So these are mostly for background. The only thing I want to touch upon in Rdf introduction is the semantics of Sparkle. And I'm only focusing on a subset of Sparkle, which is called the BGP, basic graph pattern. So a Sparkle query, as I'm sure you looked at, consists of these triple patterns. And a collection of these a query that consists of only these triple patterns, nothing else, no unions, no optionals, etc., is called the BGP, basic graph pattern Sparkle query. So if you really look at those, the Sparkle semantics is one of subgraph matching using homomorphism. And the operational semantics, how you can actually think of this, is that you go into your triple store, you find all the triples that match each of these individual triples. So on the right, this one has 5 triples, triple patterns, and on the right I have 5 lists as tables. And really the one way to think about Sparkle semantics is that you're taking joins. So because the subjects have the same variables. Sorry, I wrote this wrong. This should be subject-subject joins. You're doing a subject-subject join, and then you're doing a subject-object join, and then here you're doing a subject-object join as well. These all should be different. So that's fundamentally the only thing that you need that is important to keep in mind. The other thing about Sparkle is the Sparkle query shapes, because these come quite a bit in the subsequent discussion. These Sparkle query shapes play a role. Most of Sparkle queries are of the star shape, where you have a single vertex from which these predicate or property edges emanate. You can have trees, chains, cycles, and more complex queries, which might typically people, when they talk about these complex queries, they talk about 2-star queries or 3-star queries attached to each other, but they don't have to be only stars. They could be anything. So this one is a star, a chain, and a cycle query. Okay, so this is the only part of Sparkle that is important to follow. So now I'm going to just jump into scale-out systems, and I'm going to talk a little bit about graph partitioning, because all of these systems assume that the graph is partitioned, and then I'll talk about 3 different approaches. So the objective of partitioning, of course, and this appears in relational systems, etc., as well, is that you take your data and you somehow partition it, or sharding is what it's called. Partitioning in this case is horizontal partitioning. So you take the table and horizontally cut it and put each partition in a different worker, and then the query then executes in parallel on this one. And some of the systems that have proposed taking the triple table and simply using hashing, simple hashing on the triple table to get the partition. One of the problems with this is that when you're doing those subject-object joins, etc., you get way too many intermediate results, so your join costs increase. And in particular, when you're doing interpartition joins, these you need to move data around, and this becomes difficult. So the issue here is the triple table does not capture the relationships between the triples. So people have actually started looking at direct graph partitioning techniques, where the data is not simply a table, but it's a graph, but you have the same objective where you want to partition it into different worker nodes or machines. 2 typical approaches to this, and this is not specific to RDF, this is for property graphs as well, is either edge cut, or what we call vertex disjoint, or vertex cut, or edge disjoint. And the objectives in the graph partitioning is in any data partitioning is you want to keep the partitions to be more or less balanced, so that the workload is balanced across the worker nodes. You want, and depending on whether you're doing vertex disjoint or edge disjoint, you want to put one vertex or one edge, each vertex or each edge in a different partition. And while you're doing it, you want to minimize the edge and vertex cuts, because those are the things that either cause extra communication or state maintenance, as I will show you. Most of these techniques, graph partitioning techniques, are what I call workload agnostic. There are some techniques that take the workload into account. What if my workload consisted of this? What can I do with the graph? But the techniques I'm going to talk about are workload agnostic. So vertex disjoint partitioning puts each vertex in one partition. So this will cause edges to be cut. And we want to minimize those because each edge cut causes communication across different partitions, different worker nodes. The alternatives are hashing on the IDs of the vertices, the simple case, which gives you very balanced, and it's very fast and simple, but it causes high number of intermediate results and high number of edge cuts. And the gold standard in this in this domain is what is called the Metis family of algorithms, which basically goes by taking the graph and kind of coarsening the graph. So where you're looking at subgraphs that you represent as super vertices, and then you successively do these until you get to a graph you start from G0, you get to successively coarsen graphs to Gn, where Gn is so small, it doesn't matter the cost of partitioning. You use any partitioning technique to partition Gn, and then you start uncoarsening, going back and reflecting that partition on the full graph. That's the idea. So a very simple case where I took one graph and I used a hash function based on the vertex labels, and you get this, and all of these dashed lines are cuts, and that's actually painful. This doesn't reflect it well, and the vertex disjoint partitioning performs well for graphs with where the degrees are low, but on power law graphs, which are very common, they cause many edge cuts. And you can use Metis, but the Metis has very high computation overhead, and it really doesn't scale to large graphs. So almost all of the systems that do vertex-based partitioning, they provide hashing as part of their toolbox to go. And the important issue here is that in this case, as I'll talk a little bit later, in RDF case, what becomes more important for minimizing interpartition joins is not to minimize the edge cuts, but really to minimize the predicate cuts. And I'll demonstrate that a little later on. So I'll skip this because I haven't gone over the example, but the example is in the earlier part. In the edge disjoint partitioning case, we put each edge at a different partition, and what this causes is that the vertices are replicated. In other words, if the two edges that are placed on different partitions share a vertex, that vertex has to be repeated in both places, and that means that if the state of those vertices need to be maintained in both places. So if there are that becomes an issue. In RDF, this is less of an issue, simply because the RDF is a simple graph model where the vertices only have labels, so there isn't much issue of updating on those edges. And edge disjoint partitioning is used a lot in cloud-based systems. I'll talk about later on, because in cloud-based systems, what they do is they look at each edge with the particular predicate, and all the edges with the same predicate go into one file that goes on HDFS. And the objective in cloud-based systems is to minimize the scans. So that this allows you to focus the scans on a particular file, depending on what the Sparkle query is asking. So that's important. And again, if I take this and do it there, do the edge disjoint partitioning, I get what is on the right. And these dashed vertices are replicated vertices between different partitions. So number 2, the home partition is P2, but I replicate it in P3 as well. Okay, and these perform well on power law graphs, and they are fast and highly serializable. But the star queries are problematic because in star queries, what you want is you want the vertex and all of the edges coming, all of the neighboring vertices to be in one partition, and edges will break those up, and we might get high vertex replication. So again, the example there is one. So let me jump into the 3 types of scale-out systems I'm going to talk about. The first one is query partitioning systems. So these start with a partitioned data set. So D1 to D6 are the partitions. We've already partitioned the RDF graph. Now we partition the Sparkle query. So we get subqueries. And the idea is that we wanted to partition the Sparkle query in such a manner that I can execute as many of them. I can execute each of these as independently as I can, or on one of the worker nodes. So I try to avoid the joins that of the partial results that are created by these subqueries. So the problem is really distributed execution of these queries over the partition data. And this is really very, very analogous to distributed query processing and optimization in relational systems. And there are a number of systems of this type. The main idea of these systems that you need to keep in mind is how do I partition the data and the query in such a way that the interpartition joins are minimized. And all of the techniques that have been proposed, there's a high degree of coupling between query decomposition and the partitioning that they use. So they either say, this is the partitioning that we do on the data, and here's how you can partition the query based on that partitioning, or they say, this is how I want to partition the query, this is the characteristics that I want, and to meet those characteristics, this is how I partition the data. So 2 example systems that I'll talk about. Again, this is a partitioned graph where into 2 partitions. The amber ones are one partition, blue ones are the other, and these green dashed edges are your edge cuts. That's basically where communication between partitions goes. One system says, let's first do a partitioning using metis, but they admit that they can actually use something else that doesn't matter. This is the base partitioning that gives you a nice one. And then I'm going to replicate vertices using n hops. So if I'm using 1 hop, then in the amber one, I'm going to reach out into the blue and pick the 1 hop reachable vertices and replicate them in the amber one. Similarly, for the blue one, I'll reach out and replicate the other ones. But it could be n hop, and of course, as n gets higher, your replication cost increases. But you can evaluate more queries independently in that case. But in the extreme, of course, you don't partition it, but that's not what you want, of course. So when you get a query Q, what you look is the radius, which is really what is the distance from the query at the center that matches the center of this graph to the edge. And if the radius of the query is larger than n, then I have to partition it into several subqueries such that the radius of each subquery is less than or equal to n, and then I execute each of those subqueries on a partition. The second alternative is very similar, which is Vertex block proposal, and they were proposed 2 years apart, interestingly. They also talk about partitioning the triples across vertices, but they use what they call semantic hashing. So what they do is they first form triple groups. They say they group the triples based on whether they have the same subject, or whether they have the same object, or whether they have the same predicate. So they can have S triple groups, O triple groups, or P triple groups. And then they use a hashing function to allocate each of these triple groups into machines. And then they basically do allow replication. The idea of replication is this. So if this is your baseline partitioning, and you have this query which reaches there, this query is not independently executable, of course, because you need to take the join of the partial results over these three partitions. But the idea they have is that if I extend P1 by a little bit over, then I can handle P1 on its own. And similarly, I can extend P5 a bit, and I can handle P5 on its own. The proposal is not very, very different than the other one. It's just how they partition the query and how they partition the graph slightly changed, but the main idea is the same. We've been working on this, and this is a little bit different. This is not published yet. It's under submission. The main point of our work was the recognition that all of the previous work tried to minimize the edge cuts, but the edge cuts are not what really causes the interpartition joins. If you can increase your edge cuts, but if all of the edges that you cut involve a single predicate, they're all born on, or they are all resident or something, then really the class of queries that you can execute independently increases quite a bit. So the idea here then is that we want to instead of minimizing edge cuts, we want to minimize the predicate cuts even at the cost of increasing edge cuts. So the next couple of slides introduce how we do it. I'm not going to go through. It's the similar idea to Metis, which is that we coarsen and then we partition. But coarsening, the really important case is being able to choose the internal predicate. So how do I form the super vertices as I coarsen? And that we use a greedy algorithm that's based on weakly connected components. And we choose those the predicates, and then we partition the coarse graph on the right, and then we go back and uncoarsen the original graph. And we have a formula for we have a methodology for processing queries on it, and it gives us fairly good performance. I don't have time to go through it. So the query partitioning approaches are really quite high performance, great for parallelizing centralized RDF data, but the query decomposition is not easy, and query decomposition is difficult even in relational cases, but they're difficult here as well. And as I said at the beginning, the query decomposition and data decomposition are very tightly integrated. It would be interesting to adopt a relational distributed query processing methodology here. By that I mean that what we do in the relational case is that we do query decomposition, we do data localization. The query decomposition gives us an algebraic query. We look at how the data is allocated, and then we take this algebraic query tree, and partition it so that the joins are minimized, and then we create a distributed query plan and optimize it, figure out how to do how to put together the results. And when we execute the query on these local sites, then we execute the distributed execution plan. This is really not done in the case of the query partitioning based graph processing, unfortunately, because there isn't much work in this domain. Fundamentally, as I'll mention later on, there isn't a well-developed algebra for Sparkle. One alternative is partial query evaluation. We did this a little bit. So again, the RDF data is partitioned. We don't care how it's partitioned, but we don't partition the query. What we use is the partial query evaluation technique that programming language people have invented. So what that is that when you have a function on X, we rewrite the function as with two arguments. One is S, which is the sum of the arguments that you know, the inputs that you know, and the other one is the unknown inputs. And then we basically execute the f prime on S, on just S, to get the what is known, and we leave the D as the unknown, and we execute another function on it to get the final answer. So in our context, what are the known inputs? S, it is basically the query itself, and what we also know is all of these partitions plus the what we call the extended edges, which are really extended vertices, which are really vertices on the other partition that are at the end of crossing edges. And then from here, the idea is that we send a query to each partition. Each partition computes partial results, but these are not final results, because what we have are, we're missing these crossing matches. And then we assemble it, the final result from these partial results by a join operator. And the setup is what you would expect. A bunch of machines over which data is distributed. We do local evaluation on these machines, and then we do an assembly phase, which can be either centralized, we send the results back to where the query originated from and assemble there, or we do distributed joint processing.
So, Tamer, we've got about 5 minutes left.
Okay, I'll finish. So this has high performance due to parallelization. It doesn't have the problem to deal with the query decomposition, but you need to modify the RDF systems at each site to be able to deal with this partial query evaluation technique. The final category here is cloud-based solutions. So again, the RDF data is partitioned, and the Sparkle query is run as MapReduce jobs. This is really your typical data parallel execution. And the main idea here is that query operations are MapReduce jobs. And so you need to have a MapReduce systems that implements all of the relational operators that you might be using in this processing. And as I said, you typically do edge-based partitioning here to get across. An example is Hadoop RDF, where they split the predicates, and then they basically split each predicate. So each of these is a file. So all the triples, which has the has name predicate, are in one file, and so on. And then they do further dividing based on the object part of the graph. And then when they get a query, they first choose a particular file, and for each triple pattern, and they execute that triple pattern on those files as MapReduce jobs, and then they do a MapReduce join at the very end. So I'm going very short here because there's a very nice book that you should, you can probably, Stanford has a subscription to this, so you can download and read it. These are highly scalable systems. Again, they're inherently fault tolerant because of MapReduce, but the performance is bounded by what MapReduce can do. All those intermediate relations are that you generate is going to be causing a lot, and you have to write the results of those to HDFS and then run the join job as a separate MapReduce job, which means you have to read from HDFS again. And whatever optimizations you do, you have to do it outside of the MapReduce platform. Let me talk about federated systems. These are different. As I said, you have these RDF sources. So what you really, when in the scale-out systems, we took a D and we partitioned it into a set. Here we're going the other way. We have a set of D sub i's, and we're putting them together to get a D. And each of these D sub i's are a Sparkle endpoint, meaning that if you give them a Sparkle query, they can execute it. And you get the Sparkle query, you decompose it, you run it in each of these Sparkle endpoints, and then you compose them. And typically, you have this RDF resources, and the main idea is one of data integration. You're starting from bottom, and which are the sources, and you're going up. And you always have a control site which maintains a bunch of metadata that is about access patterns, et cetera, et cetera. And typically what you do is you do the query site, the control site takes the query, does a query decomposition and selects which parts of the query or which QI should be executed on which of the sources. You do a local evaluation on the sources. Yeah, you get the results back, and then you join the partial results at the other end. The typical way that you can do query decomposition, I'll demonstrate by an example here. You have this query. We basically determine, this can actually, you can tell from here as well, the prefix is G. These two triple patterns can be executed on geonames. The third triple pattern can be executed on any one of these, so we'll have to choose. And the last one can be executed at New York Times. So you divide these into three queries, Q1, Q2, Q3, and you execute them at those sites and then combine the results. And then you do some data localization, as I talked about. And therefore, what basically happens is exactly what I described. You take this, you determine the sites where you're going to execute it, you execute them, and you compose them. That's the federated. The question is, what if you have some which are not Sparkle endpoints, in which case you use the mediators, and you build mediators that pretend, that have wrappers that pretend that these sources can execute Sparkle queries. So they act as if there are Sparkle endpoints there. And there are examples of federation. Uniprot is one. This is an example that actually goes to multiple Uniprot data stores and gets the results. It's a service-oriented federated query execution. And the advantage is that this is data integration approach. So you take the data sets as they're given. You're not trying to do anything with them, and you go from there. But the Sparkle endpoints are notoriously unreliable. There are studies that show that at any one given time, up to 64% of these Sparkle endpoints are offline. So if you pose a query, they may be offline. So basically what you need to do is this kind of fault tolerant or query processing techniques that can withstand those the offline ones. And not all RDFs, when you do have to do mediators, that's heavy duty. So the conclusion is that there's a lot of work. I listed the systems at the beginning, but I cannot say that the technology is as mature as distributed relational data management. They're not. Part of the reason is that there are multiple communities that work with RDF. Semantic web community really focuses on functionality, much less on performance. So if they can execute queries, generally they're satisfied. And we worry about performance, but the data management community has focused more on property graphs than on RDF graphs, and that's an issue. And most work considers only BGP, but full SPARQL 1.1 has these optionals and unions and aggregation and so on. Those are really not well handled yet. We have some work that's ongoing. Algebra definitions are starting. There is a recent paper that's defining an algebra for SPARQL that I'm not sure how I feel about it yet, because I'm in the middle of studying it. But there is a prospect that if those algebras are successful, we could get somewhere. And there are a lot of opportunities for using views and view-based optimization, multi-query optimization, cost-based optimization. These are open problems that we haven't done. And the work so far only considers static RDF graphs. And as they evolve over time, how do you do incremental query processing to cope with this is not known. So I'll stop there.
Very
I think
good.
it took a few more minutes, but I apologize.
Yeah, so we still have like 9 minutes left for
Okay.
any questions. So there is
questions in the there are two questions that people have answered. One is for Tamer and one is for Petra.
Okay, go ahead.
So why don't we start with the one for Tamer? Can you explain, this is about your parallelization slide. Can you explain why or when parallelization is necessary? Thanks.
Okay. So typically you do parallelization and it comes in two places. In one of two cases. One is, as I mentioned in the federated case, there are data sets with owners, and these owners do not want to maintain ownership of their data. So they're willing to run your queries on their data, and they are willing to be part of a federation, but they're not willing to let go of their data. So that's when you do the one type. The parallelization for scale out is when the data set size becomes so high that running SPARQL queries or any query on a single site becomes a performance bottleneck. Either the data set size is too big and you cannot fit on a single machine, or the computation becomes so heavy, especially with concurrent queries running, that you want to get intra-query parallelism and inter-query parallelism, and that's when you choose the scale-out route.
Thank you. And in general, commodity hardware is much cheaper than vertically scaling systems. Thanks for that.
That's true. That's true.
The next question is for Petra. About in general question answering systems, how can you write Cypher to query a knowledge graph to build question answering systems?
Be useful to know a bit more about context around that. Is the knowledge
graph?
So
I think by question answering system, they might be meaning when the query is posed in English. So I mean, how do you go from English into Cipher?
So I think you would actually need to employ a natural language processing library to actually transform written English or spoken English and actually pull out verbs and nouns from there and map them basically to a pattern, essentially. So if you say, find me all people who have eaten at a restaurant in San Francisco, you can start to actually formulate basic patterns around that. However, that's not something I think that's actually been explored a lot. So I'd guess any effort in that area is at a very early stage. I do know of some groups that actually are working on such a thing. But in terms of actually using Cipher now without such a layer is, to my knowledge, not possible.
So I actually have a question. One is, how do we, like, if we have in RDF, if there is the same triple which resides in two different sources, how do we refer to it?
If the same triple, there is the, I didn't show in the preliminary stuff. Each source has a particular identifier, and that becomes a prefix. So in the examples that I showed, there was a G, there was a Y. So G was the prefix. It's almost like XML namespaces that you can use. G refers to geo, and Y referred to New York Times, but these are usually long URIs that you use.
So in our early lectures, we used the example of a query such as, on a map, show me all the people who were born in Winter Tour who also died there, right? So let's say you have a question like this. To answer that question, you're not going to find data in one location. So is there a system distributed Sparkle execution system out there which could answer this? I mean, all this magic that you were describing in this distributed, in the federated queries, like, is there a real federated query Sparkle system out there?
What do you mean real?
I mean, that actually, to which I could go and pose queries, distributed queries like that. You mentioned Uniprot, right? That's just one
well,
example.
I mean, it depends on I think if I understand your query, one is the one question is, how do I know which sources I need to go to?
Mm-hmm.
Right? That's not a solved problem, and that for the data management community, that's the problem outside of us. In other words, it's just like SQL. You need to know the schema to formulate a proper SQL query before we can actually worry about how we execute it. It is the same issue here. One of the and that's actually that's an active and important research domain on its own. In the following sense, even when you know sources, writing Sparkle queries beyond simple ones is not an easy task. So people have been working on natural language interfaces to Sparkle, and those might come to the rescue. But you need to know where the data is. Uniprot allows you to do it. It's a federated Uniprot knowledge graph. Combines 150 RDF data sets and allows you to write at their website even a particular Sparkle query that goes and gets it from 150, but you still have to know something about what each source offers.
Does it go to those sources in real time, or have they integrated the data in one place?
No, it goes in real time. Yeah. You can actually play around if you want to see how this works within the Uniprot context. If you go to Uniprot website, then there are example queries that you can ask them to run, and it will run it in real time and get you results. Or you can try to formulate your own query. I've never tried to formulate my own query because I don't know enough biology to be able to formulate a reasonable query. But I've played around with the sample queries that they've posed to see what they do and how they do it.
And just one more question came in again to Petra. Does Neo4j use any partitioning, parallel techniques? Is there a distributed version available, etc.?
Yes, there actually is a version in our enterprise version called Fabric, which actually, if you maybe I can provide the link to that, that actually partitions your graph using edge disjoint partitioning. I believe it's a variant on that, but I actually haven't worked on that myself, so I can't tell you much more than that. But essentially, that is a way of actually spreading out your graph across multiple databases, and that's called Fabric. I'll just send the link to that. In terms of parallel processing, that actually is something that we are undertaking and investigating within our engineering department.
Thanks.
Any other questions? Mike, you have any questions?
Okay.
Well, we are pretty much at the end of our class time, which is 5:50. So with that, I'd like to really thank our invited guests for giving us fairly detailed and thorough deep dive into both Cipher query processing as well as Sparkle query processing. And I was definitely very struck by this scalability concerns which are being addressed in this distributed and parallel query processing. And that's something that is going to be very important as these data sets are getting bigger. We are going to need these techniques for scalable query evaluation. So thank you all for coming, and thank you both for your illuminating presentations. With that, we conclude. And as far as our class is concerned, we'll continue next Tuesday. And our topic for next Tuesday is going to be how to design the schema of a knowledge graph. Thank you all.
Thank you, folks. Really appreciate it.
Thank you.
Thank you.